Welcome back to the deep dive.
Hmm.
Today, we are going to do something a little bit different.
Oh, yeah.
We are going to step out of the studio, mentally at least, and right into a freezer.
Okay.
And I don't just mean it's a bit chilly, grab a sweater kind of weather.
Mhm.
I'm talking about the kind of cold that feels, well, it feels personal.
Personal is exactly the right word. We are looking at a stack of sources today that are all centered around this very specific narrative. It involves two students, Kesser and Steen.
Right.
And the opening scene of their story is it's visceral. It's early morning, they are cycling to school, and the thermometer says -5 degrees Celsius.
Which, to be fair, is cold, but it's not, Arctic Explorer cold.
On paper, no. But here is the variable that changes absolutely everything. The wind.
A wind chill.
They are riding directly into a headwind. And Steen, one of the students, he describes the sensation of that wind hitting his forehead as being struck by Thor's hammer.
That is such a vivid image. It immediately stops being a number on a weather app and becomes, well, a physical battle.
Exactly. And physically, what's happening there is convection. The wind is just stripping the heat layer away from their skin faster than their bodies can replace it.
So it's not that the air is getting colder, it's that the heat is leaving them faster.
Precisely.
Right.
So while the air temperature is -5, the text notes that the effective temperature, what their skin is actually battling, is closer to -18 degrees Celsius.
-18. Okay, now that is deep freeze territory.
It is. And the reason we are starting here, shivering on a bike path with these two, is because this physical sensation of the cold, it sets the stage for the entire deep dive.
Right.
Kesser and Steen are on their way to a class called Nature and Innovation taught by Professor Hendricks. And as they are pedaling, fighting this headwind, they start to ask a really fundamental question.
Which is?
If we are freezing and we have high-tech coats and, metabolic heat, what in the world is happening to the ground beneath our tires?
Right. Because the intuitive assumption, the thing I think most of us believe without really questioning it, is that when winter hits, nature just shuts up shop.
Yeah, closes down for the season.
We assume the soil's frozen solid, the plants are dormant or dead, and the whole system is just hitting the pause button until spring.
Precisely. We see winter as a static state, a void. But the mission of this deep dive, based on the research Kesser and Steen uncover, is to completely dismantle that idea.
Okay.
We are going to find out that underneath the frost, there is a biological engine that is not only running, it's running a highly sophisticated thermodynamic maintenance cycle.
We aren't just talking about gardening tips here, are we? This sounds a lot bigger.
No, not at all. We are talking about physics. We are talking about, believe it or not, quantum mechanics in pine needles.
Seriously.
We are talking about fluid dynamics in the soil, and ultimately we are landing on a massive debate in soil science, the battle between the hot pile and the thin layer.
This is the part that really surprised me when I was looking through the materials. The idea that how you compost, whether you build a giant mountain or just spread it out, isn't just a matter of preference.
Not at all.
It's a matter of physics, and it's specifically critical for the type of soil Kesser and Steen are dealing with.
Sandy soil. That is the key context here. That's the variable that changes the whole equation.
So by the end of this hour, you are going to look at a messy, leaf-covered garden very, very differently.
You're going to see it not as untidy, but as a high-tech insulation system, a biological machine.
So zip up your jacket, pull your hat down over your ears to protect yourself from Thor's hammer. Let's unpack this.
Let's dive in.
Okay, I want to start where the students start. They're on their bikes, they're freezing, and they start looking at the landscape around them. And Steen mentioned something his dad told him.
Yeah, a little piece of kind of garden folklore.
He says that grass stops growing when the temperature drops below 7 degrees Celsius.
Which is a pretty standard rule of thumb in botany.
Yeah.
7 degrees is often cited as the biological zero for many temperate grasses.
Biological zero. What does that mean exactly?
It just means that below that temperature, the metabolic cost of growing, of pushing out new leaves, outweighs the energy they can produce from the weak winter sun. So they go dormant. It's an energy-saving move.
Right. But Kesser, who seems to be the one who's constantly looking for the exception to the rule,
He's the observer.
he points to the trees lining the road. Pine trees, conifers.
Yes.
And he makes this really astute observation. He says, if the grass gives up at 7 degrees, why are those pine trees still green?
It's a fantastic question.
They haven't dropped their needles, they haven't turned brown, They're standing there in -18-degree wind chill, looking perfectly fine.
It's a question that touches on one of the greatest evolutionary tricks in all of history. We take evergreens for granted, but when you stop and think about the biology, they really shouldn't exist.
Why shouldn't they exist? What's
Yeah.
the problem?
Okay, so think about what a needle is. It's a solar panel. That's its job.
Right.
It's packed with chlorophyll. And the job of chlorophyll is to capture photons' light energy and funnel that energy into the cell's machinery to make sugar. That's photosynthesis in a nutshell.
Okay, simple enough.
But here's the problem.
Mhm.
In the winter, the sun is still shining. It might be weaker, but the photons are still hitting the needle. The chlorophyll is still absorbing that energy.
It can't turn off.
It cannot turn off. It's like a solar panel that is hardwired to the grid. It's always on.
But it's freezing, as we've established.
Exactly. The chemical machinery that uses that energy, the enzymes and proteins that turn carbon dioxide and water into sugar, that machinery relies on liquid water and a certain amount of warmth to function. At -5 degrees, that machinery is stalled. It's frozen solid.
So you have energy pouring in from the sun
A constant stream of energy.
and absolutely nowhere for it to go.
Nowhere. It's like flooring the accelerator in a car that's stuck in park.
That sounds dangerous.
It is catastrophic for a living cell. In physics, energy cannot be destroyed. It has to go somewhere.
So where does it go?
If it can't be used to make sugar, it turns into heat. Or worse, it excites electrons to these really unstable states, creating what we call reactive oxygen species.
Ah, free radicals.
Free radicals, the very same things, they are molecular wrecking balls. Basically, without some kind of safety mechanism, a pine tree in winter would literally burn itself alive from the inside out.
You're saying the sunlight would kill it.
The accumulated solar energy would fry the proteins and bleach the chlorophyll white. The tree would be dead by spring.
But they don't bleach white. They stay green.
Yeah.
So what is the trick? What's the hack?
The sources point us to some incredible research from Umeå University in Sweden, specifically the Department of Physiological Botany. They uncovered a mechanism they call the solar short circuit.
A short circuit. Usually when I hear short circuit, I think of sparks flying and things breaking. My toaster, for instance.
In your toaster, yes, that's a bad thing. But in a pine needle, a short circuit is a brilliant survival strategy.
How's it work?
To understand it, we have to look at the photosystems. There are two main units in photosynthesis, two little protein machines, photosystem 2 and photosystem I.
I remember this vaguely from high school biology. They usually pass electrons between each other in a chain, right?
Correct. Normally in the summer, they are physically separated in the membrane of the chloroplast. They sit apart, passing electrons down a chain like a bucket brigade.
And that separation is important.
It's crucial. That separation ensures maximum efficiency in making sugar. It keeps the process organized.
Okay, so that's summer. What happens in winter?
This is the amazing part. The researchers found that in winter, the pine tree physically restructures its own cells.
It rebuilds its own engine.
It does. Under what they call ultra-fast fluorescence analysis, we're talking picosecond precision, trillionths of a second. They could see that photosystem 2 and photosystem I actually migrate through the membrane and physically fuse together.
They dock, like spaceships.
Exactly like docking spaceships. That's a perfect analogy. And by connecting physically, they create a brand new pathway for the energy.
A new circuit.
A short circuit. Instead of trying to force electrons into the frozen sugar factory, which is stalled, photosystem 2 just dumps its excess energy directly into photosystem 1.
So it's a bypass. And what does photosystem I do with all that extra energy?
It acts as a heat sink. It's designed to handle it. It takes that dangerous high voltage energy and safely dissipates it as harmless heat. It just radiates it out into the needle.
So the pressure release valve.
It essentially opens a safety valve to release the pressure before the system explodes. It protects the whole machine.
That is mind-blowing. The tree is literally rewiring its own solar panels seasonally.
It is, and the scientists made a point of emphasizing how fast this happens. They had to analyze the needles straight from the cold outside because if they brought them into the warm lab, they would start to undock and rewire back to summer mode within minutes.
So it's a dynamic physical restructuring.
Absolutely. And think about the implications of this.
What kind of implications?
Well, if conifers hadn't evolved this specific short circuit trick, the boreal forests, the taiga that covers these massive stripes of Russia, Canada, Scandinavia, they just would not exist. They couldn't survive the winter.
And if those forests didn't exist?
Then human history is completely different. The source explicitly mentions that the economies of the Northern Hemisphere, timber, firewood, construction, are built on this one biological innovation.
So we built our homes and heated our hearths for thousands of years because a pine tree figured out how to short-circuit its battery in the cold.
That's it. It's an incredible piece of natural engineering.
It really puts the nature and innovation into perspective. It's not just, pretty trees. It's hardcore engineering.
It is. And that theme engineering against the cold transitions us perfectly from the canopy down to the ground. Because Kesser and Steen aren't just looking at trees, they are heading to a specific destination.
Right, Oma's garden.
Oma's organic vegetable garden, their grandmother's garden.
This is the fieldwork part of their ride. And Kesser isn't just eyeballing the garden. He's brought equipment.
He has. He's brought a soil thermometer, which the text compares to a meat thermometer.
It's a familiar tool.
Exactly. And I love this little detail here about how Steen, the ever-vigilant science student, immediately checks the calibration.
He suggests checking it in ice water and warm water,
Yes.
right, to make sure it's accurate.
Yes, he says, let's check it. Ice water should be 0, warm tap water should be around 30. It's a small moment, but it's so important.
Why?
It tells us that these two aren't just guessing, they are validating their instruments. They are thinking like scientists. Once they know the tool is accurate, they can trust the data.
So let's look at the data. We know the air temperature is -5, feeling like -18 because of the wind. Kesser takes this calibrated thermometer and plunges it into the soil of Oma's garden.
And specifically, under a layer of compost. That's the key detail.
Right, under the mulch.
Yeah.
And what's the reading?
The reading is +2 degrees Celsius.
+2. Now I have to play devil's advocate here for a second. +2 is barely above freezing.
Yeah.
To me, that still sounds incredibly cold. Is that really a win?
It is a massive win, a game-changing win. In the world of thermodynamics and biology, the difference between -5 and +2 is not just 7 degrees. It's the difference between two different states of matter.
Ice versus water.
Exactly. At -5, water is a solid crystal. It's inert. At +2, it is a liquid solvent. And biology life requires liquid water.
Okay.
If the water in a cell freezes, the ice crystals expand and they puncture the cell membranes. Transport of nutrients stops. Everything halts. By maintaining +2 degrees, that soil is technically still online. It's still biologically open for business.
The source calls this compost layer a thermojacket. I like that. But how does a pile of dead leaves actually keep the ground warm? It's not like it has a battery heater in it.
No, but the Earth does. You have to remember that the ground is a massive thermal battery.
A thermal battery.
It absorbs heat all summer long, deep heat. In the winter, that heat tries to rise up and escape into the cold atmosphere. It's a natural heat flow.
Okay.
If the soil is bare, like the neighbor's garden we will talk about later, that heat just radiates straight out into the -18-degree wind. Poof, it's gone.
And the ground freezes solid.
The frost line drives down deep, freezing the soil into a block of concrete.
But the compost, the thermojacket.
The compost is insulation. It's all just trapped air pockets. Think about the down feathers in a winter coat. The feathers themselves aren't warm.
Right, they trap your body heat.
They trap air, which traps your body heat. The compost does the exact same thing for the earth. The leaves and straw trap air, and that trapped air stops the Earth's heat from escaping. It holds that thermal energy right at the surface.
So it's trapping the heat coming up from below, not catching heat coming down from the sun.
Primarily, yes. In the dead of winter, the heat flow is from the deep earth upwards. The compost puts a lid on it, and that simple lid of, garden waste keeps the entire system at +2 degrees.
And that single temperature difference drives everything else we're going to talk about. But before we get into the microbiology of it all, we have to talk about water. Because winter isn't just cold, it's often wet.
It's wet, or it has snow melt. And this is where the physics of the thin layer really shines compared to bare soil. The text uses a great contrast here. The hammer versus the sponge.
Let's talk about the hammer. This is what happens on the neighbor's bare soil.
Yes. Imagine a single raindrop falling from a cloud. It accelerates until it hits terminal velocity. It's a small object, but it has mass and velocity, which means it has kinetic energy.
It's a tiny missile.
It is. When that tiny missile hits bare, unprotected soil, all that energy is transferred instantly to the dirt. Smack.
And what does that impact do?
It physically shatters the soil structure. Healthy soil is made of little clumps, little peds, or aggregates. The raindrop acts like a tiny explosion, blowing those aggregates apart.
And why is that bad?
When you shatter those crumbs, you release the finest particles, clay and silt. These microscopic particles mix with the water to create a sludge, a slurry.
And when that dries,
As that sludge dries, It seals the surface. It forms a hard crust. The text calls it a concrete-like lid.
Like a scab.
Exactly like a scab. It becomes impermeable. So the next time it rains or the snow melts, the water can't get in. It hits that crust and just runs off sideways.
Taking the topsoil with it, I imagine.
Erosion, absolutely. But more importantly for the winter, it means the soil below that crust stays dry and compacted. It doesn't get recharged with water. And dry soil freezes much harder and faster than moist soil. It becomes a solid block.
Okay, that's the hammer. It's a
Yeah.
pretty destructive image. Now let's look at Olma's garden with the compost jacket. The sponge.
Here, the raindrop doesn't hit the soil. It hits a leaf or piece of straw or a bit of seaweed from their mix.
So the impact is absorbed. The mulch takes the hit.
The kinetic energy is dissipated harmlessly. The organic matter acts as a shock absorber. The water then just trickles gently down through the layers. It doesn't smash, it seeps.
But once it seeps through, it still has to go somewhere. The ground could still get waterlogged.
But this is where the +2 degrees comes back into play in a huge way. Because the soil is not frozen and because it is covered and has a food source on top.
The biology is still awake.
The biology is still awake, and that includes the big engineers of the soil. The worms, earthworms.
The worms are still moving at +2 degrees.
They are slow, for sure. They're not exactly zipping around, but they are active. They are moving up into the compost layer to feed and then moving back down into the soil to rest where it's safer.
And every time they do that,
Every time they make that trip, they are digging a tunnel, a vertical channel.
a macropore.
A macropore, a perfect little drainage pipe. So you have this system where the compost on top acts as a sponge to catch and slow the water, and underneath it, you have a living plumbing system of worm tunnels that conduct that water deep underground.
So instead of running off the surface, the water is stored deep in the soil profile.
It creates a reservoir. The soil remains porous, or what soil scientists call having a good crumb structure. It can hold a massive amount of water without becoming anaerobic or muddy.
It's amazing to think that a layer of mess, just dead leaves and grass clippings, is actually a sophisticated water management system.
It is, and it's a system that relies entirely on the fact that the engine is still running. If that soil freezes solid, the worms retreat deep underground or die, the tunnels collapse, and the system fails. That +2 degrees is everything.
You mentioned the engine is running. I want to double-click on that, because the source material from Kesser and Steen's class talks about these different activity zones. We tend to think of nature as either on in the summer or off in the winter. But it's not that binary, is it?
Not at all. That's a huge misconception. It's much more like a gearbox in a car.
A gearbox. Okay, I like that. Walk us through the gears.
Okay, so first you have the high gear, fifth gear, let's say. That's roughly 5 degrees C to 10 degrees C and above. This is full shop open.
Springtime.
Spring and autumn. Exactly. In this zone, everything is firing on all cylinders. Bacteria are dividing rapidly. Fungi are spreading their networks. Worms are breeding. This is where you see rapid decomposition. You put a banana peel down, and it's gone in a week.
Okay, that's high gear. But Oma's garden is sitting at +2 degrees cedar. That's well below that high gear zone.
Right. This brings us to the second gear. The zone between roughly 0 degrees C and 5 degrees cedar. The source calls this a paradox, the biological null point.
Null points. That sounds like nothing is happening. It sounds like neutral gear.
That's the paradox. That's the misconception. It's not that nothing is happening. It's that reproduction has largely stopped. The population isn't growing. The worms aren't laying eggs. But the metabolism, the actual work of eating and pooping, to be blunt, is still happening. It's just in slow motion.
So who is working this cold shift? Who are the specialists?
The specialists. The text specifically highlights woodlice in Danish. The source notes they are called bankebidaer, and certain types of cold-tolerant fungi.
Woodlice, so like pillbugs or roly-polies.
Exactly. These creatures, these decomposers, have enzymes that are adapted to function at lower temperatures. They are the low-gear crew. They're the ones who show up when everyone else has gone home.
So the woodlice are just down there shivering and chewing on leaves all winter.
Essentially, yes. They are shredding the coarse fibers of the leaves and the straw. They are the first stage processors. They are breaking down the physical structure of the compost, making it accessible for the bacteria later.
So they aren't moving fast, but they have months to do the work.
They have all winter, and because they have all winter, the cumulative effect is massive. They are essentially prepping the materials. They are loading the pantry for spring.
Loading the pantry. I like that. So that's low gear. What's the gear below that?
That's the neighbor's frozen soil. That's the pause button zone below 0 degrees C. That's not a gear. That's the engine being turned off and frozen solid. The water becomes ice, which is biologically inaccessible. The bacteria go dormant, forming protective cysts. Everything stops.
So when spring finally comes, let's compare the two gardens.
The neighbor's soil has to thaw. That takes energy and time. Then it has to warm up. Then the bacteria have to wake up from their dormant state. Then they have to start finding food and rebuilding their populations. It's a cold start in every sense of the word.
But Kesser and Steen soil? Oma's soil?
It's already running. The engine is warm. The wood lice have spent 3 months shredding the leaves into bite-sized pieces for the bacteria. The nutrients are already partially released and water-soluble. As soon as the temperature ticks up to 5 degrees C, that soil just explodes with life. It is spring ready from day one.
That is a huge competitive advantage for a gardener. It's like keeping your car engine idling all night in the winter versus trying to start a car that's been sitting in a snowbank for a month.
That is a perfect analogy. And for Kesser and Steen, this advantage is absolutely crucial because they're dealing with a specific villain in their garden story, sand.
Ah, yes. The sandy soil. I'm not a geologist, but I know sand drains well. Why is sand such a problem in winter?
Sand is a tricky beast. Imagine a jar of marbles. That's sand. There are huge gaps between the grains. Those are the macropores.
Which means water runs right through us.
Runs right through, fast. It's like a sieve. This is great for not getting waterlogged in a rainstorm, but it's terrible for holding on to things.
What kind of things?
2 crucial things: heat and nutrients. Sand has very low thermal mass compared to clay. It heats up fast in the sun, but it also gets cold very, very fast at night and in winter. It doesn't hold on to warmth.
Okay, so it freezes easily.
Very easily. And the source mentioned something really interesting about frost behavior. That frost is actually good for clay, but bad for sand.
How does that work?
Right. If you have heavy clay soil, which is made of tiny sticky particles that compact into hard clods, you actually want it to freeze. The water in the clods expands as it turns to ice, and that expansion shatters the hard clay, fluffing up the soil. It's nature's plow.
But sand doesn't have clods to begin with.
No, sand is already just loose grains, so frost doesn't improve its structure at all. Instead, the winter rains and snowmelt just wash straight through it. It's a process called leaching.
Leaching.
The water dissolves the valuable water-soluble nutrients like nitrates and minerals and just carries them deep down into the subsoil, way below where the plant roots can reach them.
So by spring, bare sandy soil is cold, dry, and hungry. It's an empty pantry.
Precisely. And this is where the thin layer compost method becomes a chemical necessity, not just a philosophical gardening choice.
How does the compost fix the sand problem?
It comes back to our friends, the microbes, the low-gear crew, the wood lice, the bacteria, and the fungi.
What are they doing that's so special for sand?
As they break down the compost, they don't just make smaller pieces of leaves, they excrete byproducts. One of the most important substances they create is something called humus.
Humus, the black gold of soil.
It is. But chemically, what matters here is that humus is a colloid. It's sticky. It has a negative electrical charge that allows it to hold on to positively charged nutrients and water molecules.
So it's like a magnet for food and water.
A magnet is a great way to think about it. But even more potent than humus is what the bacteria themselves produce. It's called EPS, extracellular polymeric substances.
That sounds incredibly technical.
It's basically bacterial slime.
Laugh slime. So we're banking our entire garden on slime.
We absolutely are. This slime is a complex chain of sugars. It is incredibly sticky. It coats the individual sand grains and glues them together into little clusters called aggregates.
So it turns the jar of marbles into a jar of, granola clusters.
Exactly. You're turning the marbles into little sponges. These aggregates create a structure that holds water inside the clump, but allows air and roots to move around the clumps. It transforms the sand from a sieve into a sponge.
So the biology is literally engineering the physics of the soil. The bacteria are building architecture.
They are building the house that the plants will live in. And this leads directly to the synergy with the no-dig method that Kesser and Steen are using. This is a huge part of their nature and innovation class.
Right. They mentioned that they start their plants indoors on a windowsill and then they transplant them out. Why is that specific part of the strategy so important for their sandy soil?
It's all about risk management and connection. If you put a tiny seed in cold, nutrient-poor sand in early March, It just sits there. It's vulnerable to being eaten, to drying out, to rotting.
But if you put it in a plant that already has roots,
You're giving it a massive head start, and you are looking for an immediate connection to something invisible but vital in the soil.
the fungal internet.
The mycorrhizal network. These are microscopic fungal networks that live in the soil. Imagine a web of millions upon millions of tiny white threads running all through that compost layer and the topsoil.
And what do these threads do?
They are master traders. They physically connect to the plant roots. The plant, which can photosynthesize, gives the fungus sugar carbon. In exchange, the fungus acts as a massive extension of the plant's root system.
How massive?
Orders of magnitude larger. It can go out and find water from far away. It can excrete acids to dissolve minerals like phosphorus from sand grains. It mines the soil for the plant.
So if Kesser and Steen were to dig up their garden rototill at like traditional farming, what happens to that network?
You tear it to shreds. It's like taking a bulldozer to a city's fiber optic network. You just destroy the infrastructure. The plant then has to spend weeks and a lot of energy rebuilding those connections.
But because they use a no-dig approach?
The network is intact. It's alive. It's waiting. The moment they transplant that little seedling into the garden, its roots touch the fungal hyphae and boom, connection established.
It's like plugging a laptop into a fiber optic cable versus trying to get a signal with an old dial-up modem.
That is a perfect analogy. The plant immediately has access to water and nutrients from a much larger area than its own roots could ever explore.
And all of this is happening under the compost layer, the thermojacket, which is keeping the surface soil at +2, protecting those new, delicate roots from night frost.
So the plant doesn't just survive the transplant, it thrives immediately. This is how they get such a huge jump start on the growing season.
This brings us to the central conflict of the whole deep dive, the great debate. We've established that covering the soil with compost is good, but there is this huge disagreement in the gardening world about how to make that compost.
This is the method A versus method B tension in the source material. It's the core of their project.
Let's break it down. Method A is the one most people know, the huge hot pile. You see it in community gardens. You pile everything up in a corner, you turn it with a pitchfork, it steams like a little volcano.
Right. This is thermophilic composting. Thermo means heat, philic means loving. You are intentionally creating an environment for bacteria that love extreme heat up to 60 or 70 degrees Celsius.
That is scalding. That's
Yeah.
hot enough to cook an egg.
It is, and people love this method for two main reasons. It is fast and it is clean.
What do you mean by clean?
Those high temperatures kill everything bad. They kill weed seeds, so you don't spread weeds around your garden. They kill pathogens like salmonella or E. coli if you're composting kitchen scraps or manure. If you are obsessed with hygiene, the hot pile is your sanitizer.
The source calls it the incinerator.
Or, to use the more colorful description from Steen, a quick fart.
So I wasn't sure if we were going to say that on air.
Hey, it's in the source text. But the analogy works perfectly. It is a fast, intense, explosive release of energy. And that, right there, is the problem.
Why is that a problem for their sandy soil?
Because where is that energy going? When you see steam rising from a compost pile, that is water, heat, and gas leaving your system.
It's leaving the chat.
It's leaving the planet, effectively. The thermophilic bacteria are burning up the valuable carbon and the nitrogen to generate that intense heat. A huge amount of the nutrients is volatilized, turned into gas like ammonia or nitrous oxide, and lost to the atmosphere.
So you start with a big pile of leaves and grass.
And you end up with a much smaller pile of very stable, very clean dirt. It's great potting soil, it's safe, but the energy is gone. The readily available food is gone.
Okay. Now let's look at method B. The thin surface layer. This is Kesser and Steen's approach, Oma's method.
This is cold composting, or more accurately, lukewarm composting. They take their material leaves, grass, seaweed, chop it up, and spread it directly on the soil. No pile, no heat.
So who is doing the work if it's not the heat-loving bacteria?
It's a totally different workforce. The source calls them the conservators, and this group is dominated by lactic acid bacteria, by yeasts, and by the native soil fungi.
Lactic acid bacteria, that's the stuff in yogurt, and sauerkraut.
Exactly. This isn't a process of incineration, it's a process of fermentation. Think of the hot pile as cooking a stew. You boil it hard, it breaks down fast. Think of the thin layer as making kimchi or pickles. It's a slow, cool preservation process.
Okay. And how does that help their sandy soil?
In fermentation, you aren't burning energy and releasing it as heat, you are preserving it. The lactic acid bacteria, for instance, slightly acidify the environment around them. This acidity chemically binds the nitrogen into stable forms. It prevents it from turning into ammonia gas and floating away.
The nutrients stay in the material, right there on the
They
surface.
stay right there on the soil surface where winter moisture can slowly dissolve them and drip feed them down to the plant roots and the soil life. And remember the slime, the EPS.
The glue for the sand.
Lactic acid bacteria are prolific slime producers. They are the master architects of that soil structure, that crumb structure, the thermophiles in the hot pile. They don't do that nearly as well. They're all about burning, not building.
And what about the worms and the woodlice? If I put a worm in a 60-degree compost pile,
It's dead, boiled in seconds. The hot pile is a sterile environment for macroorganisms. But in the thin layer, the temperature is just ambient. The worms, the woodlice, the fungi, and the bacteria all work side by side in a complex ecosystem.
so to sum up the debate, the hot pile gives you a dead, stable, clean product. The thin layer gives you a living, active, ongoing process.
Exactly. And for sandy soil, which has no structure and no nutrient holding capacity of its own, you need the process. You need the glue makers. You need the continuous drip feed of nutrients. You need the living system.
That really answers the core question of the deep dive then. For Kesser and Steen, dealing with that specific type of hungry soil, the huge hot pile would be a mistake.
It would be a huge waste of resources. They would be incinerating the very things, the glue and the energy that their soil desperately needs to come to life.
So they chose the slow marathon over the quick sprint.
And they are building a much more resilient system because of it.
Let's talk about the practical side of this, because they have a pretty clever system for managing this thin layer. The sources call it the bag lunch system,
This is a great bit of low-tech innovation. It starts with their lawnmower.
the ultimate garden shredder.
Absolutely. They take their browns, the dry leaves, which are high in carbon, and their greens, the fresh grass clippings, high in nitrogen, and they mix in a third, very special ingredient, seaweed, eelgrass specifically.
Why seaweed? Is that just because they live near the coast and it's free?
Availability is part of it, for sure, but biologically, it's a power move. Seaweed brings two critical things to the mix.
Okay, what's the first one?
First, trace minerals. Things like iodine, magnesium, boron, calcium minerals that have often washed out of our land-based soils over centuries and accumulated in the ocean. The seaweed brings them back onto the land. It remineralizes the soil.
And the second thing, this one sounds important.
Inoculation. Seaweed is naturally covered in those beneficial lactic acid bacteria. It's salty and slimy. It is a natural starter culture for the fermentation process. It kickstarts the whole system,
So they layer all this stuff on the lawn and just run it over with the lawnmower, chopping it fine.
creating a massive surface area for the microbes to attack immediately. And then, whatever they don't spread on the garden right away, they store.
In small bags, the bag lunches.
Yes. And you have to imagine these two students, cycling to school with these bags of chopped fermenting grass and seaweed. It probably sounds and smells a bit ridiculous.
They want to trade. I've got a ham sandwich. No thanks, I've got fermenting eelgrass.
But for the plants, it's the ultimate five-star meal. When they go to plant a berry bush or a tomato plant later in the season, they dig the hole and they dump a bag of this pre-digested, microbially rich mix right in with the roots.
So it's an instant boost.
It provides instant food, instant moisture retention, and an instant inoculation of beneficial microbial life right where the plant needs it most.
And the source says they can customize the bags, right?
Yes, this is the really clever part. If they have a hungry plant that needs a lot of nitrogen, like a cabbage, they'll use a greener bag with more grass clippings. If they just need mulch for a pathway or around a fruit tree to retain moisture, they'll use a browner bag with more leaves.
It's modular soil management.
It's incredibly smart. It's a low-labor, high-efficiency system that turns waste into a customized, high-value resource.
It's so simple, but it creates this highly resilient, self-improving system.
It turns the garden from a passive space that you have to constantly feed with fertilizers into a managed biological machine that largely feeds itself.
So if we zoom out from all of this, from the pine needles to the worms to the lawnmower, what is the big takeaway from Kesser and Steen's frozen bike ride?
I think it's a fundamental shift in perspective. We usually think of winter as an enemy to be fought. We fight it with heaters, with snowplows, with cleaning up the garden and leaving the soil bare.
We try to impose a sense of human order on it.
Tidiness. But Kesser and Steen aren't fighting winter. They are managing the physics of it. They accept the cold, and they use a simple tool insulation to work with it. They understand that what we see as mess, the leaves, the seaweed, the layers, is actually mechanism.
Mess is mechanism. I'm writing that one down.
It is. The neighbor with the bare, raked, frozen soil thinks he is being tidy. But biologically, his soil is crashing. It's a dead zone. Kesser and Steen's garden looks messy, but their soil is idling at +2 degrees, the fungal internet is online, and the worms are keeping the plumbing clear for the spring-fall.
It redefines what a healthy garden looks like. It's not about being neat and tidy.
It's about being alive.
So the next time you, our listener, look at a garden covered in dead leaves in the fall and you think, I should really rake that all up and make it look clean, maybe don't.
Don't. Let it be messy. Put the rake away, get the lawnmower out, chop it up, and let the engine idle through the winter.
Then maybe just wear a warmer hat than Steen did on his bike ride. Avoid Thor's hammer if you can.
Definitely protect the forehead. That's a key lesson here.
Thanks for joining us on this deep dive into the physics of the frozen ground. We'll see you next time.
Stay warm.